This is the last section in Chapter 14, the structure and acid-base properties. This particular section is pretty important because on Part 2 of the exam, there will be a writing section. The last couple of questions are short answer where you can't use your calculator. These are excellent questions that could be asked in that section. So we're going to look at the effect of structure on acid-base properties. So let's look at some models of acids and bases. There are two factors for acidity in binary compounds: bond polarity and bond strength. In other words, if the polarity is high, that's a good thing. And that is one factor that can determine the strength of an acid. Bond strength, low, is good. Weak bond strength actually means strong acids. It's kind of interesting. So let's look at some examples of what I mean by that. Here is a chart that shows 4 binary acids: hydrofluoric, hydrochloric, hydrobromic, and hydroiodic acid. You can see the bond strengths in the middle, and you can see their acid strengths. Now, you might wonder, well, why is HF a weak acid? Well, in the bond of hydrogen fluoride, and we will in another chapter be talking about bonding and shapes of molecules. Remember, this is chapter 14, and we skipped earlier chapters that will cover this. We will go back to those. They tend to be a little bit easier chapters, so I skipped them, at least the first semester. So the HF bond, as you might remember, fluorine has 7 valence electrons, and that's the dot diagram, or as you will recall, the dash diagram. That's the HF molecule. Fluorine is highly electronegative. That means it really wants to gain electrons, and of course it wants to gain electrons from hydrogen. So if this molecule right here is pulling on hydrogen in a way, hydrogen can't be released. And if hydrogen can't be released, it can't be part of an equation like this. And that's the release of hydrogen. So if the molecule is highly electronegative in this binary list here, you can see that if the strength of the bond is high, that means that the electronegative atom attached to hydrogen really holds on to hydrogen so well that it doesn't release it, and therefore it makes for quite a weak acid. Chlorine, bromine, and iodine are increasing in strength. Iodine is actually the strongest of the 3, Hi, because it has the weakest force. Weak force means it can be released easily. So Hi, which is a strong acid, can actually go to completion, 100% dissociation, because the hydrogen ions can be released. The iodine is not as electronegative. Now, oxyacids are a little bit different. These are not binary. Oxyacids are ones that contain oxygen, often a polyatomic if you want to think about it like that. And you can see here it says it contains the group HOX. Now, remember, we're going to get back to the structure of molecules at a different time. But HOX would be hydrogen, then oxygen, and then some other ion. It could be chlorine, fluorine, bromine, something else. For a given series, the acid strength increases with an increase in the number of oxygen atoms attached to the central atom. The greater the ability of X to draw electrons towards itself, the greater the acidity of the molecule. It's a little bit different than the binary ones. So here's a good chart, and you can see the first 4. I like these 4 because they all contain hydrogen and some sort of chlorine and oxygen. This is HClO3 is chloric acid. This is perchloric, chlorous, and hypochlorous acid. So they're all kind of a series with that polyatomic chlorate. Remember, per, hypo, and ite from the naming. So we can see that the first acid, the one with the fewest attached oxygens, actually has the lowest Ka value. This is quite a weak acid. So what we're saying is the ability for chlorine to pull these oxygens, or the oxygens to pull the chlorines, is pretty low. And therefore, the hydrogen is well attached to that group. As we go up here, however, you can see that as the number of oxygens increase, what's happening is the ability for this hydrogen to be released increases because chlorine is so electronegative. It has all these oxygens pulling on it. If it can pull away, then the hydrogen can kind of fall off and be released as a positive ion, which of course is indicative of a strong acid. Notice here too, H2SO4 versus H2SO3, and HNO3 versus HNO2. So in general, as the number of oxygens increase, the stronger the acid. And looking back at the previous words, whoops, let me just go back. Remember, it says, the greater the ability of X to draw electrons towards itself, the greater the acidity of the molecule. So, again, X in this first group would be chlorine, and then sulfur, and then nitrogen. So the ability for those atoms to draw electrons towards itself, the better. Notice that chlorine, if we're looking at the central atom versus sulfur versus nitrogen, I would say that HClO4 is the strongest of the three because chlorine is the most electronegative of the three elements there, chlorine, sulfur, and nitrogen. So that there is a relationship between acid strength and that central molecule which is being pulled. Let's look at the comparison of electronegativity. Again, you notice these numbers. There's chlorine, bromine, iodine, and carbon. You notice their electronegativities, and again, as the electronegativity of these central atoms increases, the Ka for the atom also increases. Oxides. We're going to be talking a bit about this. Acidic oxides, or acid anhydrides. The OH negative bond is strong and covalent. For example, in SO2, NO2, and CO2. These are called acidic oxides or acidic anhydrides. When the HOX grouping is dissolved in water, the OX bond will remain intact. It will be the polar and relatively weak HO bond that will tend to break, releasing a proton. Things that are base anhydrides is when the OX bond is ionic. For example, potassium oxide and calcium oxide. If that thing that is bonded to oxygen has a very low electronegativity, in other words, it's far to the left on the periodic table, the OX bond will be ionic and subject to being broken in polar water, including a basic solution. So these are just ways to identify substances as being acidic anhydrides or basic anhydrides when dissolved in water. And finally, the last discussion is about the Lewis acid-base model. We talked about the Arrhenius model, we talked about the Bronsted-Lowry model. There are several other models, but the one we need to know about is the Lewis acid-base model. You might remember Lewis diagrams. Those are the ones that with the dot diagrams or the dash diagrams. Again, we'll get back to those, but right here we're going to look at the definition of an acid and a base according to the Lewis model. A Lewis acid is an electron pair acceptor. Now, this always confuses me with a Bronsted-Lowry because I always think of proton donor, proton acceptor. That's the hydrogen moving. Here we're talking in a Lewis acid is an electron pair acceptor. That means two electrons are being taken in by an acid. Base is an electron pair donor. So here's a good example. We have aluminum which has a +3 charge. Obviously it has no exterior electrons, all the lower level electrons are full. And OH2, in other words, water. Now, you notice that the oxygen here has a couple of pairs of electrons. When something has a couple of pair of electrons, you can notice on the final model it has bonded to aluminum with no problem. You can see what happens. Aluminum has taken in the electron pair, and because water has an electron pair, it can donate. So in this case, this is considered a Lewis base, and this is a Lewis acid. So let's look at these three models. Arrhenius, right? Acids produce hydrogen ions, or bases produce OH. Bronsted-Lowry, hydrogen donor. Bronsted-Lowry base is a hydrogen acceptor. And finally, Lewis, electron pair acceptor is an acid, and electron pair donor is a base. So being able to recognize and discuss these kinds of things. The way I tend to remember it, for electron pair donor, I know NH3 is a base in all cases, whether it's Arrhenius, Bronsted-Lowry, or Lewis. And ammonia, if you draw the Lewis diagram for it, you can see there is a lone pair of electrons on the top of the central atom. Obviously, therefore, in a bond of some sort, ammonia is going to act like a base, because it is a base, and it will be able to donate its pair of electrons. Oftentimes, ammonia is used as an example of a Lewis base. So to help me remember the definition, and I know that ammonia is a base, I just remember that as a Lewis base, and it's the one with the lone pair, so it must have to donate in some sort of a bond. So it helps me remember the definition.